Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Unmelted asteroids, the cosmic key to life on Earth. Researchers have harnessed the chemical fingerprints of zinc in meteorites to delve into the origins of Earth's volatile elements, uncovering an intriguing narrative about the formation of our planet and the conditions necessary for life. Their findings suggest that without the influx of unmelted asteroids during Earth's formation, there may not have been enough volatile compounds, such as water and other life-essential elements, for life to emerge on the planet. This discovery not only offers insights into the early history of Earth, but also opens up new possibilities for understanding the conditions required for life elsewhere in the universe. Volatiles are elements or compounds that have a tendency to change into vapor at relatively low temperatures, playing a crucial role in shaping planetary atmospheres and surface conditions. Water, for instance, is one of the most vital volatiles, along with the 6 most common elements found in living organisms: carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These volatiles were essential to the development of Earth's oceans, atmosphere, and, eventually, life itself. What makes zinc in meteorites particularly valuable is that its composition is unique, acting like a signature or chemical fingerprint. By analyzing this fingerprint, scientists are able to trace the origins of the volatile elements on Earth, revealing where they might have come from in the early solar system. The research, spearheaded by scientists from the University of Cambridge and Imperial College London, follows earlier studies in which they discovered that Earth's zinc originated from 2 distinct regions of the solar system. Approximately half of Earth's zinc came from beyond Jupiter, while the other half came from sources much closer to our planet. This division in origin paints a complex picture of Earth's formation, indicating that the materials that contributed to the volatile inventory of our planet were drawn from widely disparate parts of the solar system. Dr. Raisa Martins, from Cambridge's Department of Earth Sciences, emphasized the significance of these findings in the quest to understand the origin of life. One of the most fundamental questions on the origin of life is where the materials we need for life to evolve came from, said Martins. If we can understand how these materials came to be on Earth, it might give us clues to how life originated here, and how it might emerge elsewhere. By tracing the sources of these volatile compounds, researchers can build a clearer picture of the conditions that fostered the emergence of life and apply this knowledge in the search for life on other planets. Central to the formation of Earth and other rocky planets are planetesimals, small celestial bodies that served as the building blocks of planets. These planetesimals formed in the early solar system through a process known as accretion, in which dust and gas particles surrounding a young star began to stick together. Over time, these clumps of material grew into progressively larger bodies, eventually becoming the planetesimals that collided and merged to form planets. However, not all planetesimals are created equal. Some of the earliest planetesimals were exposed to high levels of radioactivity, which caused them to heat up and melt. As a result, they lost a significant portion of their volatiles. On the other hand, planetesimals that formed later, after the radioactive sources had decayed, were able to retain their volatile elements because they did not undergo the same melting process. In their study, published in the journal Science Advances, Martins and her colleagues set out to investigate how the volatiles from these different types of planetesimals contributed to Earth's volatile inventory. They focused specifically on zinc, measuring its isotopic composition in meteorites originating from different planetesimals. By combining this data with models of Earth's secretion, which span tens of millions of years, the researchers were able to trace the pathways by which Earth's zinc, and by extension, its volatiles, arrived. The findings were surprising. While the melted planetesimals contributed about 70% of Earth's overall mass, they accounted for only around 10% of its zinc. The majority of Earth's zinc came from unmelted or primitive planetesimals, which retained more of their volatile elements. This discovery suggests that these unmelted planetesimals were crucial in delivering the volatile compounds necessary for life to Earth. This insight adds a new layer to the understanding of how Earth became habitable. Previously, much attention had been given to the idea that a planet's distance from its star, the so-called habitable zone, was the primary determinant of whether conditions could support liquid water and, consequently, life. While this factor is undoubtedly important, Martins pointed out that the findings of this study suggest that a planet's material composition is just as crucial. We know that the distance between a planet and its star is a determining factor in establishing the necessary conditions for that planet to sustain liquid water on its surface, said Martins. But our results show that there's no guarantee that planets incorporate the right materials to have enough water and other volatiles in the first place, regardless of their physical state. In other words, even if a planet is located in the habitable zone, it might still lack the necessary volatile compounds if it did not form from the right kinds of building blocks. The ability to trace elements through millions or even billions of years of evolution is an invaluable tool in the ongoing search for life elsewhere in the universe. By understanding how Earth acquired its volatiles, researchers can apply similar techniques to study other planets, both within our solar system and in distant exoplanetary systems. Mars, for example, is a prime target for these types of investigations. While it is currently a cold and dry world, evidence suggests that it once had liquid water on its surface. By analyzing the volatiles present on Mars and their origins, scientists may be able to determine whether it ever had the right conditions for life to emerge. Moreover, the principles outlined in Martins' research can also be applied to exoplanets, planets orbiting stars beyond our solar system. With thousands of exoplanets already discovered, astronomers are working to determine which of these distant worlds might be capable of supporting life. Similar conditions and processes are also likely in other young planetary systems, Martins explained. The roles these different materials play in supplying volatiles is something we should keep in mind when looking for habitable planets elsewhere. By studying the volatiles in other planetary systems, scientists can assess whether these worlds have the right combination of factors, such as distance from their star, material composition, and volatile content, to support life. Ultimately, this research sheds light on one of the most profound questions humanity has ever asked: how did life arise on Earth, and could it exist elsewhere? The discovery that unmelted planetesimals were critical in delivering life-essential compounds to Earth underscores the complexity of planetary formation and the delicate balance of factors needed for habitability. As researchers continue to refine their models and techniques, they will be better equipped to unravel the mysteries of our solar system's past and the potential for life on other worlds. In a universe teeming with stars, planets, and galaxies, the story of how Earth became a cradle for life is an intricate one, woven from the threads of countless cosmic events. Understanding the origins of the volatiles that made life possible on our planet is a crucial step in piecing together this narrative, a story that stretches across billions of years and encompasses vast distances. As we continue to explore the cosmos, the lessons learned from our own planet's history will guide us in the search for other worlds that may, one day, reveal their own tales of life.